So these first few, just based on what we went over last time, there's some problems with what they have up in here. So each of these is going to have something wrong. If by chance it's not wrong, then we'll just say it's not wrong. So, by the way, these are all actually very, very common mistakes, even though we go over the rules several times. On the test, we just see these a lot, okay? So, for example, this first one in the expression below, 4 is called the base, and 5 is called the exponent. Well, no, that's false. 5 right here would be the base, and 4 is the exponent. Because this would be 5 times 5 times 5 times 5. That is the base, okay? So they got this wrong. This would be incorrect. It would be the base is 4, and the exponent is 5 right here. And these two are very different, even though they look very similar.
Well, God,
All right. Yeah. Now you guys see what happened right here. What is it that went wrong on this one?
They times the base number times the exponent.
Correct. Excellent. Very good. Yeah, 2 times 6 is 12, not 2 to the power of 6. Because 2 to the power of 6 would be 2 times 2 times 2 times 2 times 2 times 2.
6,560.
What is it, 6,000?
No.
Oh, yeah, because we've seen it. Okay. 2, 4, 8, 16, 32, 64. Bam. 64 would be the correct answer.
incorrect.
So yeah, they flipped it. But can we just flip the bases and the exponents?
No.
No. There's only one way that we can do this.
Fractions.
Only for one value.
10.
If the base is 2 and the exponent
One.
is 2.
Oh, so if they're the same number, you can flip it. I see.
I guess it works for any base and exponents. They're the same. I was thinking, I apologize. It's 2 to the power of 4 and 4 to the power of 2. That's the only one that I'm aware of. But that doesn't really matter. So 2 to the power of 5 would be, let's take a look at this. 1, 2, 3, 4, 5 2's. So what was that, 32? And then 5 to the power of 2 is 5 times 5, which is 25. Very close, but very different as well. All right, what's wrong with this one? They're not the same thing, but what is different then? Yeah?
Well, you're just multiplying the 3 by the x on that one, and this one, this is x to the power of 3.
Very good, yeah. So if we expanded both of these, because multiplication is really just repeated addition.
Math didn't have rules. It would be correct because x is usually just 1x, so it kind of would be right.
Yeah, right. Exponents is repeated
Addition. Oh, multiplication.
multiplication, right? So, for example, 3x would be x plus a x plus another x. 3 x's. And then x to the power of 3 would be x times x times x. You get very different answers for any number that you put in for x right there. Okay. All right, what's wrong with this one? This one, actually, there's only a very small mistake that was made.
There's no negative.
Well, should there be a negative?
Yes.
Yeah, right. This one is, it would give us 3 negatives on it, these. So that would make the 8 negative as well. Bam. All right. Now this one, this just goes back to the stuff that we discussed last time. Negative 7 to the power of 2. How many negatives are there right there?
7. 1.
1. 1 negative. So the answer has to be a negative. 7 times 7 is 49, but it would be the opposite of 49, which is negative 49. There we go.
Because there's no parentheses.
That's correct. Yep. We need the parentheses for that to be a positive 49. As each problem is discussed with the class, make changes or add notes to your above work, which we did. Use the space below to write down important notes about exponents. Actually, we're going to look at some more interesting, fun stuff. All right, let's look at some properties of this stuff. Some of you guys have probably noticed this already. We're going to further investigate expressions with exponents by combining them through multiplication and division. But there's one thing that we need to notice about these, is that they're all going to have the same bases. They're called exponent properties or rules. So, as it turns out, you don't even have to memorize these. You can always just expand and then rewrite them using exponentials. The problems given below show the special properties that hold true for all exponential expressions. Complete columns 2 and 3 in the table below by writing each expression in expanded form and in exponential form. The first one has been done for you. As you are simplifying, try to discover a shortcut or rule that you could use to simplify more quickly. Test your shortcut. That sounds great. So this first one's been done for us, right? See how they've got these 5 3s radical, and then the 2 5s radical from this expression. Well, if we rewrote this big expression, all 5 of these 5s, well, we could write it as 5 to the power of 5. Of course, we can write the answer radical. But the shortcut for these, see how we had 5 to the power of 3 times 5 to the power of 2? And it ended up being 5 to the power of 5. So really, the rule for this one would be 5 to the power of the 3. And then what would we do with this 2 radical?
Added.
We added it. Very good. So we added the exponents. 5 to the power of 3 plus 2 is the same as 5 to the power of 5. Which is what they had radical. Let's do this next one. So let's expand first this b to the power of 6. So that's going to give us 6 b's. 1, 2, 3, 4, 5, 6 b's. 1, 2, 3, 4, 5. And then in addition to that, we got these 2 b's. So we got this 2 b's. And in between them was multiplication as well. Well, if I rewrote this with a base b, what would be its power? Well, I can count them, right? 1, 2, 3, 4, 5, 6, 7, 8. So I got b to the power of 8, but how did I do that using the rule? Well, I had a base b, right? And again, we had the 6 power, and then we added the power of 2, which gave us b to the power of 8. Alright, so you guys try this next one then. Alright, so there it is expanded. Now again, let's rewrite this though using only one base, y. How many y's were there? 16 of them, right? So what did we really do using the rule? Well, we took the first 2 y's, and then we added the next 10 y's, and then we added the next 4 y's, right? And 2 plus 10 plus 4 is 16. So again, this is just pointing out when we have the same bases being multiplied, like we did in those 3 examples, then we can add the exponents. Only if the bases are the same though, okay? So on this next one, where we've got 3x squared y times 2x squared y squared, I can't combine the y's with the x's because they have different bases, alright? And we can rearrange this. So we got 3 times 2, and then we got the x's, right? So I got this first x squared over here. So that's x times x. But then I've also got this x squared radical. And then I've got this y over here. And then I've got these 2 y's radical. So the 3 times 2, that's nice. We can just do 3 times 2, which is 6. And then the x's, how many x's do we have right there? 4 of them, right? And then we got the base y's. How many base y's do we have? 3. So 6 times x to the power of 4 times y to the power of 3. Now, of course, we did 3 times 2, but the x's, again, we just added the exponents. The 2 and the 2, and then this y right here, what's its exponent?
Itself.
Close.
1.
1. It would be a 1 right there. So yeah, we would write that in as a phantom 1 right there. Explain how to multiply exponents with the same base without expanding. When bases are the same, add the exponents. That looks better. Or wastes, either way. I don't know what the heck. Alright, so let's look at this algebraic rule. And yes, this is called the product of powers. You don't have to memorize that, but we may use it once in a while. So the base right here is x, and then we've got the exponent a, and what would we do with the exponent b? Well, we would add it to the a right there.
Should be AB.
A plus B. So, right, if A was 3 and B was 1, you'd have x to the power of 4.
Why can't they?
So let's go ahead and simplify these, and we'll use the rule. Alright, so for this first one, we see that we have a base of x, but then we got this power of 5, and then this power of 3 right here. Since we're multiplying those two base x's, we'll just add the two exponents, and that gives us x to the power of 5 plus 3 is 8. Same with part B here, we got the base x, we got the power of 40, and again the power of 3 right here. So since we're multiplying the bases, we'll add the exponents, and we get x to the power of 43. Now C is a little bit different. We got the two bases, we got A and B, but for A we've got the powers of 3 and 6, so we're going to have to add those together. See, all of this is multiplication between there as well. And then B, we've got powers of 2 and 3, so that's 2 plus 3 right here. So this ends up being A to the power of 9er, and B to the power of 5. Alright, make up your own problem that requires powers of products to simplify. So what base do you guys want to use?
4.
A. What do you want the power of A to be?
4.
4. So we'll multiply this by another base A to what power?
50.
50. Alright, so this would end up being A to what power?
A to the power of 54. 200.
54.
No.
200.
Okay, never mind.
So this next one, E, how would we simplify these? Well, it is the base A stuff, that's good. But what's the power of this A right here?
1.
1. So this would be 1 plus the 3, which is going to be A to the power of 4. Now it's common for people just to see that there's no exponent right there and just say, well, it's A to the power of 3. Well, no, we had to tack on that other A that we're multiplying. Yeah, so my recommendation is to use that phantom 1 right here. Alright, good luck. If you need help, we'll help you.
He goes,
Okay. Let's start with the x's. So there's an invisible one there, and then so there's an x here and an x there. So you want to add the 1 and the 2, which equals x 3, and there's a 2 over here. So you want to start that with the equation, and then you go into the y's. Oh, there's a 4 over here as well, which you would add to the 2, right?
Well, it's
Multiply. Oh, multiply to the 2. So that would be an 8 actually. And then you have 1y over here and a y over here, which would be y to the power of 4 times z.
Correct. Excellent work.
Wow.
You could do z with the 1 on top, right?
That's a good point. Now, if you did put the exponent for z right there, that is perfectly acceptable, okay? Alright. There you go. Good luck.
Okay. So, okay. So, well, what I did, I split it up, I guess. So I'd do A, and then because there's a phantom one basically right there, so it'd be A1, and then B5, and then 8, and then A2, and then B, and then that's basically a phantom one. So B1,
B5.
and then so you combine these, and that would be A3,
B6
and then this would be B6, and then this is the only 8. So is that right? I guess.
That's correct.
Okay, here.
Excellent work.
Wait.
Very nice. You could. So this is one very nice notation that we can use. If you do want to show the multiplication between there, that is okay as well.
Are we gonna have to do these?
We don't need to get mixed up in the different bases. We just need to look at the same bases and then combine those when it's multiplication. But be careful. It's common for us math teachers to throw in an addition in there once in a while, which means we can't combine it the way that we've been doing. So just be careful on that stuff. All right, the next rule, so today we're going to do two rules, is the quotient of pairs. So quotient means division, which is why right here we can see this division up in here. Now what we'll do is we're going to expand both of these, the numerator and denominator, and then we'll see what we can do from there. So there's our numerator, and then we'll divide it by the 2 3's in the denominator right here. Now we have to remember, what's anything divided by itself?
One.
1. So 3 divided by 3 is 1. And 3 divided by 3, as it turns out, is 1. So when this happens, see how we canceled out those 2 3's in the denominator? All we're left with is the 3 3's in the numerator, so this ends up being 3 to the power of 3. So let's look at the shortcut on that, right? So we started with 3 to the power of 5. And then the 2, we subtracted those other 2 out from the denominator, which gave us 3 to the power of 3. So yeah, when we have the same, what the heck? When the same base is in the denominator, we're just going to subtract those out. But it's only with the same bases, all right? So what about this next one right here? Well, in the numerator we got 4 A's. 1, 2, 3, 4. In the denominator we got 3 A's.
And your answer's gonna be different.
So yeah, we cancel the A's out with 1's. And all we're left with is A to the power of 1.
Or just A.
Well, or just A. Now the shortcut on these would be A to the power of 4. That's our numerator exponent. And we're going to subtract the denominator exponent, which was 3. Which gives us A to the power of 1. Alright, so the next one, we got B to the power of 3. This one's extremely different. Okay?
It's -2. It's upside down and backwards.
No, not yet.
It's -2.
So in at these, we've got 3 B's in the numerator. 1, 2, 3. And we're dividing it by 5 B's in the denominator.
And you get bigger
1, 2, 3, 4, 5. So when the B's cancel out right here, notice the 2 B's in the denominator?
Yes.
Well, what value is left in the numerator then?
0.
Because we need to be able to write something in the numerator there. We know we've got the B squared. But what's left in the numerator right here?
Nothing.
It is a phantom 1.
What?
So as it turns out, phantom 1s have many uses. Just like it did in this one with the A's. See, if you tag on a phantom 1 right there, you could say A to the power of 1 over 1. It's the same idea there. So on at these, we can still use the rule. We got base B's. The exponent in the numerator was 3. And we're going to subtract the exponent in the denominator, which was 5. Well, what's 3 minus 5? -2. So we end up with B to the power of -2. Now we'll get more into negatives here in the future, but this is the same as this. Alright, so let's expand this next one. Now we've got 2 bases, 4's and x's for both of these. Alright, so we've expanded at these. Let's go ahead and start canceling stuff out. There's a 4 and 4. We got 4 x's canceled out. So we end up with 4 to the power of 3 times x to the power of 3. And how did we get this? Well, we did 4 to the power of 5 minus the 2. And then we multiplied it by x to the power of 7 minus the 4 in the denominator. And that's how we get this stuff right here. Alright, explain how to divide exponents with the same base without expanding. So the rule radical, here we've got a to the power of m over a to the power of p. So this is going to have a base a, and then we've got the m and the p, and we just subtract those two exponents. Alright, so let's simplify these. So radical, we've got 6, and then we're going to multiply it by c to the power of 5 minus the 2, so 6 times c to the power of 3.
Hey, that rhymes 6 times.
Oh, jeez.
Rhyme too, 6 times.
Alright, what about at these? So we got bases of a, b, and c, and a has powers of 7 and 1, so minus the 1, we can show the 1 right there. And then the b has a power of 10. And then we'll subtract the 3. The c actually doesn't have anything to subtract from, so we'll just take that back and put it in the denominator radical. So overall, we still have the c in the denominator, but we have a to the power of 7 minus 1, which is 6. And we got b to the power of 10 minus 3, which is 7. There it is. Oh yeah, sorry, I did forget the squared on the c though. Alright, this next one we've got bases of x and a y. So the x we got 20 minus 15. And the y would be 15 minus 14. So we end up with x to the power of 20 minus 15 is a 5er. And then y to the power of 15 minus 14 is a 1. Alright, you guys take a moment, try these, and then we'll show you the answers. Bam, there are the answers for these.
I just put the 2, I didn't put